So we're going to look at 4 things that affect the reaction rate, and we're starting off with concentration. So as you can see from the pictures here, this one here is more concentrated, and so they're closer together and they'll bump into each other more. So increase in the concentration increases the rate at which the particles collide. Remember, we never stopped there from collision theory in the previous video. More collisions lead to an increased chance of colliding with enough activation energy is better, and colliding in the correct 3D orientation. Increasing pressure is a form of concentration also. So if we halve the volume, increasing the pressure. Okay, so I have to teach this to 9s, 10s, and 11s. And so sometimes it gets a little bit frustrating. So I've gone a little bit over the top here with describing and explaining. So I don't think a textbook or internet site can do better than this. So I'm just going to read it. It is quite detailed, and it's quite often to get a graph and you have to describe or explain. Now, I haven't used data, of course, which in your IA, if you go to the IA topic, you'll get a better idea of how to properly describe a graph. But this is just going through the theory at the moment. Okay, so we have the original concentration and we have half the original concentration. So this is some sort of reaction releasing carbon dioxide gas. Okay, so as time increases, the mass of CO2 produced increases. However, the rate of increase slows over time until it reaches a maximum. The reaction with less reactant produces less final product. Explain. Rate is initially faster as the reactant particle concentration is higher, causing more frequent collisions. More collisions increases the probability that a collision will collide in the correct 3D orientation and with enough activation energy, and so form a product. As time proceeds, there are fewer reactant particles causing fewer collisions, and so a slower rate of product formation. It reaches a maximum when all the product has reacted. The reactant at half concentration, hence, not only has an initial slower rate of product formation than the full concentration, as shown by the less steep gradient, it also has a lower maximum due to less total product formed. Try and beat that one, Mr. Textbook or Mr. Internet site, okay? I'll put the challenge out there. There's a lot of keywords and a lot of things said in there, okay? So I can't do better than that, I'm afraid. Okay, next one is surface area. Okay, so this one, the analogy is the Spartans. If you've watched 300, I think the movie's called 300, they ball up into this little turtle thing here, and so no arrows can get through the shields, right? And then someone, I think they're exposed at the back or something, someone betrays them, and then they get broken up, separated, and so there's more surface area. There's shield can't cover everyone if they're all broken up. So if you do a perimeter, add the perimeters up on here, the surface area is much greater, or just do the surface area on 1 centimeter cubed block versus 2 centimeters by 2 centimeters, 1 centimeter by 1 centimeter versus 2 centimeter by 2 centimeter. And the surface area is greater if the particles are smaller. Much, much, much greater. Okay. Increasing the surface area increases the area for particles to contact, therefore increases collisions. Increased collisions increases chances the collision will have enough activation energy to react and collide in the correct 3D orientation. I've set activation energy in the graph bits, but here I've just gotten lazy and said energy. So say activation energy. So you can see here there's an increase initial rate of reaction for the smaller chips, and they reach the same maximum. So the trial with less surface area has a less steep gradient. That's this one. Both graphs increase in product formation over time and decrease in the rate of formation until the same maximum product is obtained. If you wanted to, you could talk about concentration and add another half a paragraph to increase the size of this essay from the concentration stuff. So there is some overlap to explain the curve. And remember, I asked you to watch the experiment where it actually does this for one experiment. There's an experiment video on the website, thiosulfate. So the trial with smaller marble chips have the property of a larger surface area compared to the larger marble chips, both being the same total mass. A larger surface area increases the probability of reactants colliding, and so also increases the chance of a collision reacting in the correct 3D orientation and with enough activation energy. So as you can see, I've gone over the top and done a much better job with these graph explanations. As time proceeds, there are fewer reactant particles causing fewer collisions, and so a slower rate of product formation. Both graphs reach the same maximum as the total reactants to products is the same concentration. Okay, now to the third, temperature and rate of reaction. So temperature does two things. It increases the number of collisions just because it's moving faster and they hit each other more, but temperature also has energy to it, so it innately helps give the particle enough activation energy. So temperature is a really complicated one. Okay, so increasing the temperature increases the collision, but also increases the number of particles that will have sufficient activation energy to react. Before I get to the graph, you need to be able to draw and explain Maxwell-Boltzmann curves. And so if this is the activation energy here, if you increase the temperature, you'll see that you'll have, so this is the same number of particles in each. You can see at 100 degrees, almost like 80% of the particles have enough activation energy to react, but at 0, none do, or maybe one particle. Okay, as the temperature increases, the more molecules have enough activation energy for the reaction. This increases the probability of a successful collision. The rate of collisions also increases. So let's go to the over the top describe explain graphs here, and you can see there's a faster initial rate of reaction for the temperature than the colder one for the higher temperature. All right. So the lower temperature has a less steep gradient. Both graphs increase in product formation over time and decrease in the rate of formation until the same maximum product is formed. Both graphs reach the same maximum as the total reactants to products is the same concentration. The higher temperature has particles of higher average kinetic energy. This means they are not only moving faster, they're also colliding more frequently, causing a faster reaction. They also have intrinsically more energy to overcome activation energy. Hence, they not only collide more frequently, they are more likely to collide in the correct 3D orientation and with enough activation energy to react. As time proceeds, there are fewer reactant particles causing fewer collisions, and so a slower rate of product formation. Both graphs reach the same maximum as the total reactants of products is the same concentration. This is a little bit repetitive. Basically, I'm saying it curves off why it constantly gets slower over time. And so next, and the final one is catalysts. So the next video will go into a little bit more detail on catalysts, but basically catalysts are not used up in a reaction. They decrease the activation energy, therefore increase the number of particles that have sufficient energy to overcome the activation pathway. I've talked about catalysts before. They do. Another thing to say is they do this by creating intermediates or transition states. So they decrease the activation energy, therefore increase the number of particles that have sufficient energy to overcome the activation energy and react. In enzymes, an induced fit causes more strain on the bond enthalpy, therefore lowering activation energy pathway, or creating intermediates as well. Enzymes can do both of those things, and inorganic catalysts do as well, just not as well as enzymes do it. Okay, so last graph here, more catalyst. This one's a bit complicated because it's to when the catalyst reaches its maximum ability, maximum rate, which is extremely high for an enzyme, but not so much for an inorganic catalyst. So the trial with less catalyst has a less steep gradient. Both graphs increase in product formation over time and decrease in the rate of formation until the same maximum product is formed. Hope this is getting repetitive, and you can say it in full detail when you asked to. All right, the more catalyst available increases the contact with reactant particles. These particles are the ones with the lower activation energy and are hence more likely to react. That lower activation energy may be due to a transition state or an intermediate, and hence more likely to react when they collide in the correct 3D orientation. Next video is on catalyst. So if you didn't get those two terms, don't worry. As time proceeds, there are fewer reactant particles causing fewer collisions, and so a slower rate of product formation. Both graphs reach the same maximum as the total reactants products is the same concentration. Okay, time for a summary. Okay, so there are two main things going on. So collision theory has 1, 2, 3. They must collide. There must be correct 3D orientation and enough activation energy. Okay, and so what we have here is concentration or pressure mainly increases the collisions. Okay, so and because there's an increase in collisions, there's a greater probability that it will be 3D and activation energy will be sufficient in that collision to be a successful collision. Surface area is the same deal. More surface area, the particles can collide with each other, and there's more of them, and there's more area for them to hit rather than the sides of the container. So it's the same deal. It's all to do about the number of collisions. Now, temperature is both, really. It is also increasing the number of collisions, blah, 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 down here. Therefore, the collision has more collisions means there's high probability it's correct 3D or activation energy for a successful collision. Now, for the second part is activation energy. When you increase the temperature of the particles, they also have more energy, and so that means they actually have more activation energy. So even though they do this, they also do this. So they're doing two things. Okay. Now, catalysts, interestingly, are this one and this one. Okay, so they don't really help collisions, but as you saw from the enzyme there, they are either lining their molecules up and maybe even physically joining the other one in as well. If it's an inorganic or organic catalyst. So they're providing the correct 3D orientation. And they're also lowering the activation energy because they will, when they join this molecule, they're causing strain, which makes it easier for it to break. Or they're producing an intermediate, which we'll go into catalyst in the next video. And so by creating, instead of doing this, they're doing this. They're creating some sort of intermediate, so the overall activation energy is lower. Okay, so that's pretty complicated when you have a careful look at which part of the collision theory these four factors are helping. Okay, so I hope that's helpful.